Hi folks, it's David Kearns here with another With a Sharpie video for you today. Today's video is going to be a little bit different and a little bit technical, but I will try and make it as straightforward as possible so that the less technically inclined among you can follow along. This is going to be about modeling systems, and I want to specifically talk about the developments in machine learning, a branch of artificial intelligence which has been more widely applied these days than ever before, and how it might be useful for modeling systems that engineers typically deal with. So I'm a chemical engineer by background. I've had a lot of experience in modeling chemical processing systems, things like oil refineries, as well as power stations. There's also modeling of things like car engines or any other engineering system you might want to mention. And I wanted to give you a background on what you can get through applying these new ideas around machine learning. So to build a bit of a picture for you, let's just start with what a conventional model looks like. So conventional model I'll represent by a box here. Okay, so that's a conventional model. What is a conventional model? What does it do and what's its purpose? Its purpose ultimately is to make predictions, so to come up with some values, mathematical values or numbers ultimately, that represent or model the performance of a real system. So if we build a model, for example, of a power station, some of the predictions that a conventional model of a power station might come out with would be things like how much power is it going to produce given a certain set of temperatures and a certain fuel. What sort of things go into these models in conventional systems? So typically the way that engineers have been trained to build models, we put a number of inputs into our models when we build them. So the first one might be fundamental laws. So that could be things like the first law of thermodynamics, which enables energy balances, maybe mass balances, maybe Maxwell's equations if you're modeling an electrical system. On top of that, we feed in some assumptions. So assumptions are basically anything that you can't measure or it's hard to measure that you might need to go into your model. We often make assumptions that certain things are constant, or maybe that there are certain factors around the way that our system works. We also add into here the fundamental laws and assumptions don't give us everything we need. We usually need data to feed in, and a common source of that is empirical data. And that can come in the forms of, let's say, physical property data. Maybe it's thermal conductivities, maybe it's heat capacities, things of that nature. Sometimes they're relationships. So vapor-liquid equilibrium in distillation is a common example. And you can get those from many sources. The point here is that empirical data is usually either data or relationships which are worked out based on experiment. So someone has gone to a lab, done some experiments, and worked out that, that there are certain relationships that you can estimate things on. And then finally, and this is probably the most important one for most models, is operating data. So if you want to build a model of a real system, you have to model the way it really works. So a power station, for example, might be running at 75% of its peak capacity. So one piece of operating data is, well, it's operating at 75% of peak capacity. And that would translate to a certain amount of fuel going into the power station. Maybe you'll have different values for steam pressures within the Rankine cycle within a power station. And so that's important too. Now, these models can be used for a couple of purposes. So one of the purposes they can be used for is for design. So let's say a system that we're modeling doesn't exist yet, but we would like to build one. But in order to be able to build one, we need to know certain things about it. We need to know what materials to make it out of, how big is it going to be, what shapes or geometry is it going to take. And to do all of that, we need to be able to make predictions about how will this system perform compared to what it is that we actually want it to do. So say I'm designing a new chemical reactor, I need to know how big that has to be, what its volume is going to be. I could guess, I suppose, but that's not a very sensible way of going about things. So instead, we build conventional models of chemical reactors based on what we know about empirical data like reaction rates, fundamental laws like mass balances and energy balances and so on. They lead to predictions. They let us come up with a design. And they work very, very well for that. One of the things to bear in mind, though, is that these numbers that we get for our designs are a little bit fuzzy. And we'll get into the reasons why shortly. But the main reasons that they're fuzzy is that these models are not perfect. They do not perfectly represent the way that our real engineering systems work. And so we'll come back to that in a moment. The other reason that we might want to use predictive modeling, I beg your pardon, is for existing plants or existing system. So, and you might think sort of off the top of your head, well, why would you want to do that? Why would I need to make predictions about something that I can just go out into a plant and measure things directly? So there's a few reasons you might want to do that. You might want to do that because you want to see what will our plant do when we push it into new operating conditions. Maybe we'll change some operating pressures, maybe we'll change a different fuel, maybe we'll model its performance on a really, really hot day where its cooling system is not as effective. It's good to be able to predict these things in advance so that you can make sensible decisions about how you operate a plant. Now, we start to run into a bit of an issue here. I mentioned before that when you come up with these predictions, they're often a little bit fuzzy. Now, for design, we cope with that by implementing engineering margins, or safety margins, you might call them. So let's say in my example before, we come up with a design, we decide that a chemical reactor has to be 3.5 cubic meters is our prediction. But we know from experience that actually these models maybe are not that accurate. There's some uncertainty around them. And so we might add 20 or 30% of extra volume. So in practice, we're actually building the real thing a little bit bigger than what our predictions tell us. We don't ever build things right down to the wire because our models do have a little bit of uncertainty. But for an existing system, we actually have a way to check. And that check is we have a real system. So this is the real operating plant. So it could be a real power station, it could be a real chemicals plant or whatever. And that is producing operating data. So that operating data comes from instruments that are measuring things. So they might be measuring flows or temperatures or pressures or gas compositions or whatever it is, lots of different numbers. And so now what we have is we have a conventional model of our plant and a real plant operating side by side. We can actually compare these predictions and this operating data. There will be differences between these. I'll represent these by the delta symbol. Delta is the typical symbol that's used to represent a difference. And so in reality, what we would like is we would like our real system to be modeled as closely as we reasonably can by our model, but there will be errors. There will be differences between our predictions and operating data. The reason that there are differences, there's quite a few different reasons. Maybe our empirical data is not very good. So we've looked it up in a textbook or online, and it's not actually taken from a source that's just like our situation. Maybe some of our assumptions are flawed. Maybe the instruments that are measuring our operating data here are a little bit out. They have a bias or a little bit of uncertainty. We expect that the fundamental laws will always be correct. So the first law of thermodynamics is not violated, for example. So that means we can't create or destroy energy. But it may be that the measurements that we take in our plants to measure those energy flows, maybe they're a little bit out. And so what can we do? Well, we can go through a process known as data reconciliation. It's not something that's done very often, but if you've got models for a real system that are absolutely critical, what a data reconciliation does is it's a statistical process where we can actually tweak the parameters of our model so that they line up nicely with the operating data. And I'll give you an example. Let's say my real system has measurements of operating data, so that might include the flow in, so flow into a system and a flow out. And if everything's running steady, there's no accumulation in the system, those two numbers should be the same because we can't create or destroy energy. But let's say in practical terms, this is measuring 103.6 tons per hour, and over here it's actually measuring 102.7 tons per hour. And you say, well, hang on, what's happened here? Why are they different? Well, the reason that they're different, there could be a few reasons. Maybe there is actually a little bit of accumulation in the system, and so this flow in is actually, maybe there's a leak that we haven't actually picked up in our model. Usually we don't assume that there's leaks. So maybe there's a leak in the system. Maybe one of these or both of these flow measurements are biased. So maybe this one's reading a little high, maybe this one's reading a little low. So there's quite a few reasons why the numbers that come out of a real system don't line up nicely with the numbers that come out of our model. And so what a data reconciliation process can do is it can allow for uncertainties of measurements. So we could say, for example, that our flow measurement might be plus or minus 2%. It might say that temperature measurements are plus or minus 1 degree Celsius. These would be, say, a 95% confidence interval. Maybe our pressures are plus or minus 1 kPa. And so what a data reconciliation process is, it can actually do a mathematical adjustment on each of these measure values to try and get them to line up with what the model says. And what we end up with at the end is essentially a model which is tuned more closely to the behavior of the real system. So there you go, that's a conventional modeling approach. Quite a bit of work there, as you can imagine, going through the laborious construction of a conventional model, doing all this thinking around the inputs that go into that model, and then going through a data reconciliation process just to get something that lines up nicely with the way that your real system operates. There is another way, and that's the one I want to talk to you about now. It's machine learning. And so in the next segment, I'll talk to you about machine learning and how machine learning works. This has been David Kearns with another With a Sharpie video. Thanks for watching.